You know that feeling when you're updating your phone or maybe just using an app you rely on every single day, and suddenly it just freezes.
Oh, yeah. The
Right.
absolute worst.
Right. The screen locks up, you lose whatever you were working on,
Mhm.
and you're just left staring at your device thinking, like, we have been building software for over half a century. Why are there still bugs?
Yeah, it's a totally fair question.
I mean, it really feels like someone, somewhere, should have figured out a mathematical formula by now to guarantee that a piece of code will just never, ever crash.
Well, the wildest part of that thought is that the formula actually exists.
Wait, really?
Yeah, I mean, we literally have a mathematical blueprint for perfect bug-free software. It's this field called formal methods.
Okay.
And the core premise is that you can treat software not as a craft or an art, but as a rigorous mathematical theorem.
Ah,
You can scientifically prove that a system will behave exactly as intended under every conceivable condition.
yep.
So, no crashes, no data leaks, no catastrophic failures.
Okay, wait. If we have the math to build literally perfect software, why am I still force quitting my browser twice a week?
That is the exact right question to ask.
Right. Like, Hello Wayne actually recently wrote this fantastic piece asking exactly this question. The article is called, Why Don't People Use Formal Methods?
Yeah.
And we've got this whole stack of notes in front of us today for this deep dive, breaking down his investigation.
Yeah, it's a great piece.
Because it just feels insane to me that we possess this blueprint for perfection, and almost nobody in the software industry actually uses it.
Right. And the answer involves kind of peeling back multiple layers of how the tech industry actually functions in the real world. Like technical difficulty plays a massive role, obviously. But diving into Wayne's research reveals that the real barriers are, well, their economic realities, sheer human psychology, and just the fundamental disconnect between how our messy, ambiguous human brains work versus the hyper-literal nature of computers.
Yeah, I definitely want to get into the psychology of it later, but just trying to understand the landscape of formal methods from these notes gave me a massive headache.
I don't blame you.
Like, the author describes the formal methods community as, I love this quote, tiny bands foraging in the steppe. That does not exactly paint a picture of a well-oiled, standardized scientific machine.
No, it really doesn't. But it's a brilliantly accurate metaphor. I mean, there is no singular unified field of formal methods.
Right.
Academia tends to incentivize researchers to build entirely new, super niche systems rather than collaborating to standardize existing ones.
Oh, because everyone wants to publish their own paper on their own new thing.
Exactly. So you end up with this highly fragmented landscape. Two developers might both say, hey, I use formal specification, but they could be using completely incompatible tools, languages, and just totally different philosophies.
Okay, so to save you, the listener, from getting lost in those weeds, let's establish some clear boundaries for this deep dive.
Good idea.
The source material basically divides the field into two broad concepts,
Right.
specification and verification.
Yep.
So specification is writing down the precise, unambiguous rulebook of what the software is actually supposed to do.
Oh.
And verification is the mathematical proof that the software actually followed that rulebook.
Spot on. And we have to apply those two concepts to two entirely different targets, which are code and design.
Right, code and design.
Yeah. So code is the raw material dash, the actual lines of Python, C++, P, Java, whatever, that run on the machine.
Mm-hmm.
Design is the high-level architecture. It's the abstract blueprint of how, say, databases and servers talk to each other, which you plot out before a single line of code is even written.
Okay, so we're going to tackle those one at a time, splitting our conversation firmly into code and design. But before we look at code, I have to ask you about airplanes and medical devices.
Right.
Because there's this popular myth the author mentions. People just assume that if software controls a pacemaker or an airplane engine, the developers must be using these mathematical formal methods.
Yeah, that's the high assurance myth.
Right.
We desperately want to believe that life or death software is mathematically proven to be flawless. But Wayne's research points out that this is wildly optimistic.
Which is terrifying.
Yeah, a little bit. The vast majority of engineers in high assurance fields do not use formal methods. What they actually rely on is just massive amounts of redundant testing, rigorous simulations, and strict regulatory oversight.
Okay.
So they're testing the software until they're extremely confident in it, but they aren't mathematically proving it.
That is slightly terrifying, to be honest. But it sets up just how rare this math really is in the wild.
Exactly.
So let's look at code formalization first. If I decide I want to mathematically prove my code is perfect, step one is writing that specification, right? I had to define what perfect even means.
Right.
But imagine I can't just type, hey, computer, make sure this list of names is sorted.
No, definitely not. A computer has absolutely no concept of what sorted means, because human language relies on shared context. But formal specification demands absolute rigid logic. So you have to translate the concept of sorted into a mathematical rule.
How does that even look?
Well, for a list of numbers, you would have to explicitly define that for any two positions in the list. Let's call them index I and index j if I comes before j. Then the number at position I must be less than or equal to the number at position j.
Wow. Okay, so you really have to break the universe down to its most atomic logical parts.
You really do.
And the notes show that developers basically fall into 3 different camps for how they wrote these specs.
Yep.
So the first camp uses independent statements. This is where you write your normal code in one file, and then you open a completely separate file to write complex mathematical theorems about that code, using tools with names like Isabelle or ACL2.
Right, which, as you can probably guess, creates a massive maintenance burden.
Oh, I'm sure.
Because if you change a single line in your code file, your separate math file might completely break.
Oh.
Yeah, forcing you to rewrite your theorems all over again. So this friction led to the second camp, which actually embeds the specifications directly into the code itself.
Okay, this is called design by contract, right? Tools like Spark or Daphne.
Yes, exactly. You write preconditions and postconditions directly above your functions in the code. You're essentially weaving the mathematical guardrails right into the fabric of the software.
That makes sense.
Yeah, it was originally formalized as Hoare logic back in the 1970s, and it actually remains the most popular approach in the industry today because it keeps the rules and the code in the exact same place.
Okay, then there's the third camp, which uses type systems. And the author mentions a mathematical principle called the Curry-Howard correspondence, where they encode math theorems as dependent types.
Mm-hmm.
I'll be honest, the terminology here gets incredibly dense. What does encoding a theorem as a type actually look like in plain English?
Okay, think of a child's wooden shape sorter toy.
Okay, the one with the blocks and the holes.
Exactly. You have a square hole and a square peg. In normal programming, a type just means telling the computer, hey, this variable is an integer.
Right.
That's a very big generic square hole. Any whole number can fit through it. 5, 0, -50. But with dependent types, you can change the physical shape of the hole based on mathematical rules.
Oh, interesting.
Yeah, so you don't just say this is an integer. You say this is an integer that must be greater than 0.
Okay, so if my code tries to pass a -1 through that hole, it's like trying to smash a star block into a square slot.
Exactly. The compiler physically cannot build the program. The mathematical theorem is baked into the very geometry of the language. Languages like Coq and Agda use this to make illegal states literally unrepresentable.
Okay, so we have these 3 intense mathematical ways to define what our code should do. But Wayne brings up a massive red flag here. What if we specify the wrong thing?
Yeah.
Okay, let's say I write a flawless mathematical proof that my code perfectly sorts a list of users. But my customer actually wanted an app that, I don't know, delivers hot soup.
Right.
I've built a mathematically perfect sorting algorithm for an app called Uber for Soups that makes absolutely no sense.
This highlights the critical difference between verification and validation.
Okay.
Verification asks the machine, did we build the code perfectly according to the blueprint? But validation asks the human, did we draw the right blueprint for what the customer actually needs?
Wow. Okay.
Yeah, and critics of formal methods often point to this. They argue that spending months proving code is pointless because business requirements change every Tuesday.
It makes sense, right? Why spend a year building a mathematically flawless bridge if the client suddenly decides they want a tunnel?
Exactly. The whole agile development philosophy is built entirely around that exact problem, validating early and often, but the author pushes back on this criticism.
How so?
Well, just because you iterate quickly doesn't mean mathematical verification is useless. It just means you should delay using it until the core features are totally locked in. Furthermore, while we might not know exactly what new features a customer wants, we absolutely know what they do not want.
Right. They don't want their data corrupted.
Right.
They don't want a banking app that accidentally transfers their money to a stranger just because of a memory leak.
Exactly. Basic stability and security are universal requirements. Once you know the code needs to be stable, you can write the spec. And that brings us to the actual act of proving the code matches this spec.
Right.
Which is where the real nightmare begins.
Okay, so let's talk about this nightmare, the Dijkstra era. In the early days, pioneers like Edsger Dijkstra would literally just write out manual mathematical proofs by hand on paper.
Yeah, paper and pencil.
They would look at an algorithm
Yeah.
and try to logically argue, step by step, why it would always work. But human brains are notoriously bad at this, right? The text points out estimates that roughly 20% of published peer-reviewed mathematical proofs contain errors.
Yeah, 1 in 5. Which perfectly frames that famous Donald Knuth quote Wayne includes in the piece.
Oh, I love this quote.
Yeah, Knuth wrote out an algorithm, published it, and added a little note for his readers that said, "Beware of bugs in the above code. I have only proved it correct, not tried it."
That is hilarious.
Yeah.
The math said it was perfect, but he knew better than to trust his own human logic without actually running the code on a machine.
Exactly.
So naturally, the industry decided to take the flawed humans out of the loop. They started building computer programs to check the math theorem provers, dating all the way back to a system called automath in 1967.
Yeah.
But asking a computer to check your math introduces a bizarre new problem, which is that computers don't actually know anything about reality.
Right. Like if a human mathematician sees a basic equation, they automatically apply foundational laws. They just know that addition is associative.
Right, that 1 + 2 + 3 is the same regardless of what order you add them in.
Exactly. A theorem prover does not know that. To use one of these early systems, you had to manually define the most basic laws of mathematics from scratch before you could even begin proving your actual code.
So you either have to spend weeks proving that addition works, which sounds exhausting, or just tell the computer to assume it works, which kind of ruins the integrity of the proof.
Yep.
Or, I guess, buy a pre-built library where
Yeah.
someone else already did the foundational work.
Yeah, lucky.
And even if you get past that, the programming languages themselves actively fight against you.
Oh.
The C++ example in the text completely blew my mind.
Oh, yeah. C++ is a perfect case study in how physical reality breaks abstract math.
Right.
In mathematics, numbers go to infinity. If you have the largest possible integer and you add one, you just get a bigger integer.
Right.
Basic math. But in C++ A's, an integer takes up a specific physical amount of memory on a silicon chip. If you take the maximum possible value, which is called int max, and you add one to it, the hardware physically runs out of space.
And it causes what they call undefined behavior. So the computer might roll the number over to a massive negative value, or it might just crash completely. So your mathematical proof assumes you have a bigger number, but the physical reality of the code just broke your entire system.
Exactly. This is the immense friction of verifying code. You also run into concepts like aliasing, where two different variables in your code secretly point to the exact same piece of data in memory.
Okay, the analogy for aliasing that helps me understand this is, it's like having two different remote controls for the same television.
Oh, I like that.
Right, you pick up the black remote, thinking it controls the radio, and you turn the volume down. But it's actually synced to the TV, and suddenly your movie goes silent.
Yes.
If a mathematical proof doesn't realize those two variables are tethered to the same object, the proof is entirely invalid.
That's a great way to explain it. Aliasing is so notoriously difficult for theorem provers to untangle that computer scientists actually had to invent an entirely new, deeply complex branch of mathematics called separation logic just to handle it.
Wow.
Yeah. The fundamental dilemma here is that mathematics relies on creative leaps and assumed context, while computers require unforgiving, rigid literalism. Right.
The more expressive and flexible a programming language is, the harder it is to prove. But the easier language is to mathematically prove, the harder it is to write any useful consumer software in it.
Okay, but with modern computing power, I assumed we would have automated most of this pain away by now. Like things like the SMT revolution satisfiability modulo theories around 2006.
Right, SMT solvers.
Tools like Microsoft's Z3 came out. And from my understanding, this basically takes a creative math problem and turns it into a giant Sudoku puzzle for the computer.
That is a highly effective way to visualize it. Instead of asking a human to creatively deduce a proof, an SMT solver breaks the logic down into thousands of tiny constraints.
Okay.
It tells the computer, hey, variable x must be greater than 5, less than 10, and it cannot be an odd number. Then, the solver uses raw computational horsepower to brute force its way through all the possibilities until it finds an answer that satisfies all those rules.
Or mathematically proves no answer exists.
So with Z3 and all this computational power doing the heavy lifting, I assumed a massive tech company like Microsoft could just churn out verified code at scale. But then the source text brings up the IronFleet project from Microsoft Research.
Oh yeah, IronFleet.
They used advanced SMT solvers and a cutting-edge language to build a verified distributed system. It was hailed as this spectacular achievement.
And it was. It was a massive leap forward for the field. But the cost was absolutely staggering. It took the IronFleet team 3.7 person years of highly specialized labor to write 5,000 lines of verified code.
5,000 lines. Over almost 4 years. If you break that math down, they were writing 4 lines of code a day.
Yep. And in the world of formal methods, 4 lines a day was celebrated as a blazing fast land speed record.
You're kidding.
I'm not. The previous champion was a secure operating system kernel called CL4, and they averaged roughly 2 lines of verified C code a day.
2 to 4 lines a day. Okay, this answers the core question of why nobody uses this stuff. Because how on earth could any normal business afford to pay a team of PhDs to write 4 lines of code a day?
They absolutely cannot. Which brings us out of the theoretical math and into the harsh economics of correctness. Getting a piece of software to be 90 or 95% correct is exponentially cheaper than forcing it to 100% mathematical perfection.
It's like buying a titanium bank vault to protect a half-eaten sandwich.
Exactly.
If you're building a standard consumer web app, spending 3 years to guarantee 5,000 lines of code is an absurd waste of resources. It is infinitely cheaper to just let the app crash occasionally and fix the bugs when users complain.
Right. And Wayne references studies showing that the vast majority of catastrophic outages in distributed systems aren't actually caused by complex mathematical paradoxes.
Really? What causes them?
They're mostly caused by simple, preventable errors that could have been caught with just slightly more comprehensive unit testing. You do not need a theorem prover to catch a typo in your error handling logic.
Yeah, that makes sense. The text also highlights the cleanroom method, which completely blew my mind. You can apparently achieve near-perfect software without mathematical proofs and without even running standard unit tests.
Yeah, cleanroom software engineering is this fascinating psychological pivot.
How does it work?
Well, instead of letting developers write code and constantly run it to see what breaks, Cleanroom relies on meticulous documentation, rigorous analysis of how data flows through the system, and massive, intense group code reviews.
So by taking away the crutch of just hitting run to see if it works,
Yeah.
you force the developers to mentally execute the code in their own heads.
Yes, they have to deeply internalize the logic. Teams using the cleanroom method have historically reduced defects to less than 1 bug per 1,000 lines of code in production.
Wow.
And they hit those numbers with delivery times that match or even beat standard development teams.
Okay, so human rigor can get us 99% of the way there. But if a company still wants mathematical guarantees without being limited to 4 lines a day, there's a middle ground Wayne discusses called partial code verification.
Right. Instead of trying to prove that a program does every single thing the business spec demands, you lower your ambitions.
Okay.
You just prove that the program won't do something catastrophic. You don't prove the hot soup app routes the driver perfectly. You just prove the app's memory won't spontaneously corrupt itself.
Which is huge. And newer programming languages are actually baking this directly into their compilers, right? Like Rust mathematically proves memory safety so you can't accidentally overwrite data.
Yep.
And Pony proves exception safety. They've made partial verification highly usable because the developer doesn't have to write separate math proofs. The language just does it for them automatically.
Exactly. So that covers the reality of verifying code. It's exhausting, it's slow, and economically unviable for total perfection. Though, like you said, partial verification offers a great compromise. But earlier, we established that formal methods is split into code and design.
Right, the blueprints.
Yeah. So what happens if we stop trying to mathematically prove every single brick in the building and instead verify the architectural blueprint?
Design specification and verification. So when you zoom out, you stop worrying about how a specific integer is stored in memory, and you start worrying about how entire servers and databases communicate.
Exactly. And the author uses a high-level logging system to illustrate this. A business requirement might simply say, all system messages must be logged. It sounds completely straightforward to a human.
But the second you try to architect it, the ambiguity just punches you in the face.
Oh, yeah.
Do you mean every message you ever sent?
Yeah.
Or just the ones that successfully reach the system? Are they logged exactly once?
Mm-hmm.
What happens if the server crashes while writing the log?
Right.
What if the message contains sensitive data that violates GDPR?
Exactly. Human language hides massive architectural potholes. If you don't formalize your design, you won't discover those edge cases until the system is already built and failing in production.
Which is an expensive time to find a bug.
Very. So to fix this, engineers use design languages like VDM, Z, or TLA plus R.
TLA Plus is the one that really stands out in the notes. AWS famously used TLA Plus to verify the design of their cloud architecture, and they uncovered incredibly complex 35-step critical bugs.
Yeah, bugs that require dozens of specific servers to fail in a very precise order. Standard testing would essentially never catch them.
Wow.
Another massive success was Pamela Zave using a design language to prove that chord, which is a heavily relied upon distributed hash table, was actually fundamentally broken at its core design level.
Okay, but if they were finding these massive architectural bugs, how are they proving the designs? Because if they have to write manual Dijkstra-style math proofs for an entire AWS server farm, we are definitely back to the 4 lines a day nightmare.
Thankfully, verifying designs allows us to bypass manual theorem proving entirely and use a tool called a model checker.
Okay, what is that?
Well, a theorem prover requires a human to creatively deduce a formula, right? But a model checker is pure brute force computation. It looks at the abstract design, generates every single possible state the system could ever be in, and checks if any of those states violate your rules.
Oh, I love the analogy that crystallized this for me.
Yeah.
Theorem proving is like trying to write a flawless mathematical formula to guarantee a labyrinth has an exit. But model checking is just releasing millions of digital mice into the labyrinth, letting them run every possible route at lightning speed, and seeing if any of them get permanently stuck.
That is perfect. And if a digital mouse does get stuck, the model checker hands you the exact path it took. It gives you that explicit 35-step counterexample showing exactly how to break your system, which makes fixing it incredibly straightforward.
That sounds like an absolute superpower. But releasing millions of digital mice has to come with a massive performance cost.
It does. The fatal flaw of model checkers is state space explosion.
State space explosion.
Yeah, the number of possibilities grows exponentially. Imagine you have a design with just 3 simple processes, and each process only has 4 steps. Depending on how they interleave, you instantly have 4.3 million distinct behaviors.
Wait, 4.3 million states to check from just 3 basic processes.
Yep.
A modern app has thousands of processes interacting constantly. The math on that state space must exceed the number of atoms in the universe.
It scales to terrifying numbers very, very quickly. But the way the industry solves this is by doing what tech always does, throwing absurd amounts of computing power at it.
Oh, of course.
You spin up a massive cluster of AWS servers and let them crunch the possibilities for a few hours. It becomes a raw horsepower problem rather than a human labor problem.
Okay, let's take a step back and look at the whole picture here. Design verification abstracts away the tedious code proofs. It uses model checkers to brute force the edge cases. It hands you the exact steps to fix your architecture. And it has undeniably spectacular successes at places like Amazon. So why isn't every developer on Earth using this?
Because, as Wayne powerfully concludes in his piece, while code verification is a technical problem, design verification is a deeply ingrained social problem.
Designs are not code, and developers only care about code.
Exactly. There's currently no way to automatically generate your final code directly from a verified high-level design, a problem known as synthesis. Furthermore, there's no easy way to prove that the code your developers eventually write actually matches the verified design, which is called refinement.
So you can mathematically prove your blueprint is perfect, but the construction crew can still build the house upside down.
Precisely. Programmers inherently mistrust any software artifact that isn't the code itself.
Oh, sure.
It's the exact same cultural phenomenon that explains why software documentation is always outdated, or why architectural diagrams are ignored. If a document is not forcibly synchronized with the code, developers view it as an untrustworthy distraction.
Right. There is this massive cultural inertia. Programmers already use tools like test-driven development, or they sketch out diagrams on a whiteboard, and they feel like that's, good enough. Learning a complex mathematical design language just feels like a barrier to actually doing their jobs.
Yeah, and this is the central irony of formal methods. The greatest advantage of formal specification is that it forces human beings to sit down, debate, clarify, and deeply document exactly what they are building before they write a single line of code. It forces intellectual honesty.
But that exact strength is precisely why programmers reject it. They want to
Exact.
get their hands dirty. They want to see things compile and run on their screens, not sit in a conference room debating the abstract mathematical philosophy of a logging system.
Right. It requires a fundamental shift in how developers view their own profession. And cultural shifts are infinitely harder to execute than technical ones.
Absolutely. Well, we have covered a massive amount of territory today.
We really have.
To quickly synthesize this for you listening at home, we started by asking why we don't just use math to make our software perfect. It turns out formal methods allow us to do just that, but the field is deeply divided.
Right.
Verifying the actual code is a mathematical nightmare, where the physical limits of hardware break abstract proofs, leaving elite teams writing just 4 lines of code a day. Verifying the high-level design is much more practical, using model checkers to brute force bugs out of the architecture. But developers culturally reject it because they hate dealing with anything that isn't raw code.
Yeah. And when you look at all of this, the technical friction, the economic costs, the cultural rejection, it leads to a really fascinating realization.
What's that?
The ultimate bottleneck in creating flawless software isn't our computing power, and it isn't our theorem provers.
The real bottleneck is us.
It's us. It is the inherent messiness of human cognition.
Wow.
Think about trying to write a mathematical specification to identify something as simple as a bird or a park. You can easily show a child a picture and they understand it instantly. But trying to translate the abstract, fluid essence of a park into rigid Boolean logic is nearly impossible.
Because human concepts are blurry. Our intentions are ambiguous, highly dependent on context, and they're just constantly changing.
Exactly. But machines are unforgivingly literal. They demand absolute binary precision. So the most difficult bug in software engineering isn't a misplaced semicolon or an overflowing integer.
Right.
The fundamental bug is the translation process itself. It's the vast, murky gulf between the beautiful ambiguity of human intention and the cold, unyielding logic of the machine.
So I guess until we can figure out how to mathematically map the chaos of the human mind, we're just going to have to accept that our screens will occasionally freeze.
Yeah. The next time your browser crashes, don't just get mad at the developers. Take a moment to appreciate that you are witnessing a fundamental collision between human messiness and mathematical reality.